models as we get there. But again, my philosophy is that if you understand the basic models well, only then you understand the advanced model. So I'll spend a little bit of time on some of these frameworks. Again, if I'm going faster, please feel free to stop me, ask questions. Okay. So in this module, we'll talk about methods that are useful for data analysis. Again, we're talking about these methods in the context of public transit, but you can apply these methods widely. You can apply it in transport safety, you can apply it in travel demand modeling, and various other contexts. So any data that is of this form, you can use this method. So some of these methods have application outside transportation also. There are people in marketing, in biostatistics, and other fields who are also using some of these. So we'll start with the simplest of all the methods, the linear regression model. Again, most of you would have seen this, or even if you did not estimate it, you would have at least used it in application. So in regression analysis, what we're doing is you have a continuous variable, you have a dependent variable such as number of trips or vehicle mileage or income or various variables like that. So they become the y, and you are trying to relate that to different independent variables. Independent variables could be, for example, if you're modeling income, education level, age, gender, kind of industry they work in, all of these could be independent variables. So you simply write y is equal to beta naught, a constant, plus beta 1 x1 plus x2, and so on. So it should look something like this. So this is how the equation looks like, and we are trying to figure out from the data what the values of betas are. Okay. So if you look at your data set, you will have an important aspect of linear regression is that none of these coefficients can have powers. So the betas cannot have any powers. X's can have powers. If you want to use time square, that is okay. You can take the square of the variable and use it as a new x, that is still linear. But you cannot have powers for this coefficient. So if you have a relationship like this, on first glance it might appear like you cannot do a linear regression model because you have powers there. But what you can do is take the log of this, and once you write it in this fashion, you will write ln x1 as a new variable x3, ln x2 as a new variable x4, and this is your beta naught or constant. So then this becomes a linear regression. But if you cannot transform in this fashion, and it can happen in some cases like that, where you still have x power 1 by alpha or something like that, beta power 1 by alpha, in that case, you cannot apply linear regression. But you can still apply non-linear regression approaches. They are not, they don't fall into the linear regression. So this is an example of a log linear model. Again, in the example I showed the data in the last afternoon session, we took log y because y has a very large range. We made the range smaller by taking the logarithm of it, and we used it. You can also use other forms of linear models. So the simplest form of a linear regression model is a binary regression model, where you have only the constant and one independent variable. Okay, so I only have x as an independent variable. So for example, y is the number of trips generated, x is one experimental variable, beta naught and beta 1 are coefficients we want to estimate. So y is known to us. Okay, we collected data, we have information for let's say 1,000 people. What is their observed number of trips? We also collect their x. Okay, so independent variable x, here in this case is one experimental variable. Let's say it is how many cars they own, for example. So you have a column of y's, you have a column of x. What we are trying to figure out is the values of beta naught and beta. Okay, these need to be estimated. We don't know beta naught and beta. Okay, so usually we do this using data, and because we cannot collect data for the entire city, let's say we look at this at a trip generated by a household, we cannot collect data on every household in an urban region, so we do sampling. So what happens is when you take a sample, you cannot have 100% confidence and say, oh, this coefficient is 3.8. You could do that if we collected data from the entire population. If we collect for the entire population, then the coefficients that we estimate are what are called population parameters. Okay, but because we do sampling, there is a possibility that our sample might be representing the population, but there are variations. It's not like you're doing it for the full sample. So if I change my sample, let's say I collected 1,000 data points, and then I go back in a couple of days and collect 100,000 data points. Now, if I estimate by beta naught and beta 1, will the beta naught and beta 1 be same across the two samples? They will be different. Okay. So it's not enough to know what the value of beta naught and beta 1 is. We also want to know what is the variability of beta naught and beta 1. What I mean by that is, so I spent 1 crore rupees collecting data. I built a model because I have 5,000 household samples. I did a lot of work with. Now, if all I know is the coefficient values, if somebody else collects another set of database data, the whole project should not be a because your coefficients are at the end of the day random numbers because it's tied to the same. I take 5,000 households, I get beta naught and beta 1. It could be, let's say, 1.5 and 2 points as an example. If I take another 5,000 sample, again, I'm not saying it will become minus 1.5 and minus 2.5. It won't become that way, but it could be 1.3 and 2.7. So what we are seeing is there is a population value for the coefficient, but because we are taking a sample of observations, we are trying to get as close to the population value as possible, but recognizing that there is some variability in the coefficients. So in addition to recognizing and evaluating the value, we also would like to estimate a confidence interval on the parameter. That is important because if the confidence interval, if your parameter is such that it can vary a lot, that is not very good because if sample 1 gives you 1.5, sample 2 gives you minus 1.5, sample 3 gives you 2, sample 4 gives you minus 2. If you get a variable like that, that variable is not really useful because it is changing, the coefficient is changing with the sample. So that tells you that the variability for that coefficient is too much and that variable should not be used in your model. Okay. So while the most important part in any model is estimating coefficients, it's also very important to understand whether those coefficients are stable or not. Okay. So we call this, are we able to pin down the parameters efficiently? That's what we're trying to do when we estimate models. If you are not able to pin down a parameter for a particular variable, maybe we should drop that variable. Okay. So that's what we'll be talking about as we go. So we'll write this in matrix form because most of the operations are connected in matrix form for all models, linear regression. So here, if you have a coefficient system like this is called a multiple linear regression model because I have more than one independent variable. Okay. So here I have x1 through xk, independent variables. The corresponding coefficients go from beta 1 to beta k. This epsilon is the unobserved error or noise in your data. So what happens is you assume that epsilon follows a normal distribution and the sum of epsilon across all the records goes to 0. So there is noise in the data, but it is unobservable noise. Okay, if it is observed, we can calculate it as one of the independent variables. So the mean of epsilon is 0. Okay, there is a standard deviation, we estimate. Okay, so here I am just writing this equation in the form of matrices here. So y includes n observed values of y. X will have a column of constants and x1 through xk as columns. Okay, each of them again will have n rows. Beta is just beta naught to beta k, so you have k plus 1 parameter here, and then you have epsilon going from, there is 1 per record, 1 to. Okay. So now I can write this equation like this. It's simply y is equal to x beta plus epsilon. Okay, I'm just multiplying the matrices y, you get x beta plus epsilon. Okay, now this is the true population beta. Okay, even in the true population beta there is an error, but when we try to estimate it, what we do is we replace y with y hat because y hat is what is used to represent the prediction from our model, and beta hat will be our coefficients we estimate. So we call it y hat will be equal to x beta. Okay, so we're trying to get to this. So now what we want is Yeah, it is because yes, it should be 1 because beta naught multiplied with 1 by. Okay, so beta naught is your coefficient. The independent variable, implicit independent variable there is 1. So that's why this is column of 1s. Okay. So now you can write this as y hat is equal to x beta hat. And how, whenever we have a data, so let's say I give you a data set. I have column like this where I'm telling you what the y's are. So let's say this is number of trips 6, 5, 3, 12, 8, 7. You have that data for this. And x1, x2, x3 could be number of people in the household, number of cars in the household, location, whether it's urban or rural location, income level. So all of these could be your independent variables. Now, how can you find the betas? What will you try to do? How can you solve for betas? Can we simply do a system of equations and solve for them? Why not?
It becomes very complex to solve with a lot many curves.
Okay, so basically you have n rows of data. So usually n will be in the order of 100 or 1000, right? So you have 1000 equations. There are only probably 10 unknowns. Okay, so it is an overly defined system of equations. So you will not have a unique solution. If you try to find the 10 parameters, you will not be able to find because you will have infinite number of possibilities that you look at. So what we are trying to do is we won't be able to solve it as a system of equations. So what we'll say is, okay, I know I cannot find a perfect solution because there cannot be 10 values that satisfy all 1000 equations. You won't be able to find it. So what we do is we'll say, okay, let me try to get the next best possible. What we can do is my prediction error should be as small as possible. Right? So I want to find 10 values. Yes, it won't, I mean, if you get lucky and it perfectly matches all 1000 records, great, that's your solution. But it usually does not happen. In real world data sets, it never happens. So we started, okay, let me try to minimize my error in the prediction. So because again, at the end of the day, the reason we're developing these models is to understand the relationship between y and x. So we want it to be as accurate or as close to the reality as possible. So we simply start with minimizing y minus y hat. Y is the observed value. Y hat is computed as x beta hat. Okay? Like this. So our error is simply this. Our objective now becomes minimize that. So should I just minimize y minus x beta hat? If I directly minimize the difference, some of the differences will be positive, some of the differences will be negative. So when you add it, everything will become 0, right? So you don't want to do just the direct difference. So we use the square difference to ensure that both negative and positive are penalized. Okay. Now, one part is, okay, why can't we use an absolute function? Okay. Theoretically, that is also valid, but I don't know if you guys remember your calculus enough. If you do differentiation of the absolute function around 0, it's a discontinuous function, and this discontinuous function don't work well. So we don't want to do anything with discontinuous functions because it breaks down all the asymptotic theory that we use. So what we'll do is we prefer the square. Okay, theoretically you could have tried with absolute also, but the square works better. Okay, because square function is continuously differentiable, so you can take the first derivative, second derivative, whatever you want, you can take, and that helps us in some estimate computation. So what I'm doing here is, so we'll take the square. So in matrix notation, square is nothing but transpose times the other one. So it is y minus xb hat transpose times y minus xb. Okay, so this would be what we're trying to minimize. Trying to minimize, I want to find a beta hat that minimizes the difference between the observed vector of y's, and the predicted vector x beta hat. Okay. So I want to solve for beta hat that gives me the least error in that data set. Every data set might have differences. Okay. So again, because it's a simple function, you start with minimization. I'm just expanding these terms. I'm just multiplying the matrices here, and I'm expanding this. And then, because it's a minimization, I'll try to differentiate with respect to beta hat because I want to estimate beta hat. I want to find out what the value of beta hat is. So I'll differentiate this term these three terms with beta hat. The first term, y hat y, is the observed number of trips. It has nothing to do with beta hat. It's a constant. So when I take the derivative of y hat y with respect to beta, it will be a 0. Okay? Everybody okay with that? Because y is the data. This is given to you. This does not change with beta. Right? So this is known to us. X is also known to us. So these are observed information. So if I take, so these two will be constant in our equation. So when I come to take the derivative of this function, derivative of this will be simply 0. Okay? When I come here, I only have beta hat. This can be treated as a k. It's a constant. Right? X dash y is a k. So derivative of beta hat is 1. So you'll get 2x dash y here. There is a square of beta hat here. Effectively, when you take the derivative of that, you'll get 2 beta. So you get 2x dash x beta. So this, on the other side, we set that, we take the derivative and set that to 0, right? So we're setting that to 0. So now you get 2x dash y is equal to 2x dash x beta. What I need, I want to find, you can cancel the 2 off. I want to find the beta hat. So I pre-multiply x dash x on both sides. So I just want to make, so I sent this that side. So x dash y was there here. Then what I did is, I cannot just do 1 over, so I have to do inverse because it's a matrix. So I multiplied this with x dash x whole inverse in the front. So this becomes beta hat, and I'm multiplying that. So you get a formula for beta hat, which is a function of x and y. So I know x, I know y. So I can find my beta hat using this formula. All I have to do is do some matrix multiplication inverse. Clear? Any questions? So if you are given your columns of data, if you have your y and x, you can find beta. You just need x because you just need to compute x dash x whole inverse x dash. And again, this formula is very easy to remember. And you'll notice this is the only model which has the formula for beta. Okay, every other model is too complex to be able to solve in this fashion. You won't get a solution for your issue. So your beta hat has a clear solution. Anybody does the model, any software you use, you should get the same result. To the third decimal, fifth decimal, whatever, but it's hard beyond that. It's okay.
Y hat y minimum function. Yes. Y dash y. Y is a constant. However, y dash is actually in terms of x and beta.
No, not y hat. Y. Y is still a constant. Yeah, so y dash also, so it's just, instead of putting it as a column, y dash is a row. So y dash y is also a constant. So let me give you an example here. So let's start with a simple y and x. Okay. So let's say I have y. My model is y equal to beta 1. So there are no independent variables. I just have a constant. So a vector of 1s. So my x would be this. Everybody okay with that? Okay. So now in this case, let's try to find what is beta 0. Okay. So beta 0, beta is x dash x whole inverse x dash y. So I have x. What will be x dash? X dash will be a row of 1s. Okay. So row of 1s times column of 1s. If I multiply both of them, matrix multiplication, 1 times 1 plus 1 times 1 plus 1 times 1 n times. So it will be n. Okay. So you see that here? Everybody okay with that? So x dash x is n. X dash x inverse will be 1 over n. It's only a scalar, so its inverse is just 1 over. Then let's do x dash y. X dash y is again vector of 1s times y. So 1 times y1 plus 1 times y2 plus 1 times y3 simply be y1 plus y2 plus y3 plus y. Okay. So you end up with summation of y. So now let's apply the formula x dash x whole inverse x dash y. So this is n. Inverse will be 1 over n. This is summation of all of that. What does this show you? What is 1 by n over sum of y? Simply the mean. Right? So if you want to know what is the constant in your data set without any independent variable, just take the mean. You take the mean of your y's, that is your constant, and this would be the dumbest guess we can make. If I give you a data set and tell you these are the trips people data of trips people are making. If I tell you, okay, a new person is being brought into this data set, what would be your guess? You should say, yeah, take the average of what is observed right now. That should be our starting. Now, why is this important? Because any so-called model we develop should give me an error less than the error from this down model. Otherwise, why do I need your model? If your error is more than this, I don't need that model. I can blindly tell you what the answer is. Okay? So that is why we start with this. Because this gives you the average number of trips. So if the average you observe is 3 trips, if a random person is brought into the list, your starting point will be, yeah, this person also will make 3 trips. Because that is the estimate we have based on the data. Okay. Now every time you add a new variable, you should be improving your error. What I mean by improving the error is reducing. So you want to make the error smaller and smaller. And this becomes our benchmark model. Any estimation we do, we come and say, okay, this gives an error of 100 units, let's say. So if I do a new model with 5 variables, if it gives me more than 100 units, don't even tell me what you did, throw it up, it's wrong. Okay, if it's less than that, then I'll start thinking about, okay, you got 95, okay, I'll think about whether it's good enough or not. But you have an upper bound on the error, and this is what forms the basis for any goodness of fit measurement we do with these models. Okay, any questions? Okay, so I'll show you an example model run and desktop in my office. How many of you use remote desktop? But I love it. I connect from anywhere, and so I know where everything is on my. I have some OCD on that, so I have my computer and I work only on that. Simple data set. I'll just show you model. I'm running linear regression. I'm modeling number of trips. So this is my dependent variable. Then size and then number of paths. So again, in this case, it's just running it in this fashion. I want to show you some outputs. I'll keep showing you this again, but we'll get back. Here, this is where the coefficients are printed. So you get a value for a constant which is minus 0.232. Number of persons in the household is 2.184 coefficient, and number of automobiles is 0.826. Okay, so this is what I'm showing you. So what that means is, interpretation wise, we can start with, as the number of people increase, what should happen to number of trips? Okay, it should increase by 2.18. Okay, yeah. So what this tells you is, first thing we are looking at is, okay, it has a positive effect as expected. As the number of persons increase, the number of trips will increase. Same thing with number of automobiles. More cars, more trips people need. Okay, and both are positive. Now, one of the things to understand is, so far what we did is I solved for these values, just doing x dash x whole inverse x dash y for these 3 columns. You have a column of ones, column of households data, column of automobile data for each household, and you have the y's. We use that and got it. But what we have not talked about is Okay, how do I know if this is statistically significant? All of you have used that word, and you would have written papers also. What does it mean to define it? Okay, so for that we need to understand, again, as I said, these are random variables, which means they have a distribution, they have a mean and a standard deviation. The interplay between the mean and standard deviation determines whether that coefficient is significant or not. Okay, so that's what I want to talk about. It is something not very complex, but I think it's important to understand this as we move forward. So I'll show you some things here. We have a normal distribution function because we are assuming that our error term is a normal distribution function. A normal distribution, so I'll show you some characteristics. Again, nothing to memorize. There's a probability distribution and a cumulative distribution for them. This is how a normal distribution would look like, right? So depending on different needs, so I have three distributions centered around 0. It's a symmetric distribution, nice bell shape. If the variance is small, okay, sigma square equal to 0.2, here the variance is that it hugs around the 0. Okay, so you see that when the variance is 0.2, everything is very closely around the mean. When the variance keeps increasing, the height of the curve keeps coming down. Basically, I'm hitting it from the top, like I'm making it wide, right? So I'm banging it down, it keeps coming down. The higher the variance, the lower is the height, and we have larger spread. Okay? Here, the green one is simply another example where I moved the mean. I moved the mean to -2 with particular variance of 0.5. Okay? So again, this is just to show how normal distribution would work. Now, if our parameters are random variables, okay, which means they have a mean and variation, which would you want them to be? You want them to look flat or tall? What would you want from your parameter? Right? You want them to be tall because that means they have a very narrow range. The predominant number of density of these values will be around the mean. What we are estimating in our model is the mean. Okay? So if they are flat, like this for example, the mean is 0, it can go with significant probability to -2 or +2. That's too much variation. But if it is tall, okay, we got it 0. Okay, it can go with some probability to -0.5 +0.5. That is close. So that tells you this relationship has some promise potentially that you can capture. Okay, so I'll formalize that. That was the PDF. This is the CDF. So again, some more characteristics. So if you have mu and sigma as your mean and standard deviation in normal distribution, if you go 1 sigma to both sides, okay, from the mean, you're traveling 1 sigma to the left and 1 sigma to the right, that will capture about 68% of the observations in that distribution. If you go to 2 sigma, you will cross 95. If you go 1.96 sigma, you will get 95%. If you go 3 sigma, you get to 99.7%. Okay. Obviously, how much distance do you have to go to get 100%? Can we ever get 100%? No, right? Because infinity. If somebody tells you I am 100% sure this model works better than something, yeah, they're lying. Nothing in statistics is 100%, right? That's a good thing and bad thing. Because of that, you also can use statistics to say whatever you want to say, but usually you can never say anything with 100% confidence. The higher the confidence you want, the width of the distribution keeps increasing. Okay, so if you want to be confident at only 68%, I'm only going 1 sigma on both sides. But if I want to be confident at 99.7%, my distribution goes 3 sigma on both sides. So the larger the confidence you want, the higher is the width of the confidence. It looks counterintuitive, right? Like, if you think about speed, you're doing a study of speed on the road, and you want to tell 90% of the time what is the speed limit versus 95% of the speeds observed, and then you want to do it 95% of the time. If you want to do it 99% of the time, each time you want higher confidence, the band keeps becoming larger and larger. Okay, so you might say at 99%, the distribution I see on the road goes from 20 kilometers to 60 kilometers. That's not very useful, right? After a point, the band becomes pretty useless because you're saying I'm going from 0 to 100. I mean, what kind of information is available in that band? Everything physically possible is part of the band. So that's why you have to, there is a trade-off between what kind of confidence you want and what will be the output that you want to get. Okay. So let me show you an example there. So I want to show you this one. So let's say we have this as our equation. So the true equation for this case, let's assume, is the number of trips is a function of household size and number of cars. Okay, only two variables. So now what I want to understand is whether beta 1 and beta 2 are significant. So in hypothesis testing, we start with the assumption that variable has no impact. Okay, the idea is you want to prove to me beyond doubt that this variable has an impact on my. Okay, you are not saying, if by default you are not assuming that a variable is important. So you might say, oh no, household size should be important. Okay, then let's prove it. Only if you prove it, it's like the court of law. Okay, everybody is presumed to be innocent. Okay, even if they are Donald Trump. So if only you have to prove, I know it's recorded. You have to prove it beyond doubt that that person is that committed the crime. Okay, so same thing in statistics. Everything has no impact. You have to prove beyond doubt that that variable has an impact. So that way, we are ensuring that we are not taking every variable that pops up in your model as important. We are actually ensuring that we have a high level of quality control to make sure these variables are really significant. Okay, to do this, so let's say we have this variable. So you have the coefficient, which is our mean, and you ended up, you computed a standard error. This is computed in SPSS for us. So we have this value in any software for that matter. So if I plot this distribution, so this is the standard error, so variance would be square of that. I plotted this distribution. What you will notice is predominant area under the curve is to the right of 0. Right? So it's actually 90.998. So 99.8% of the curve is to the right of 0. This is kind of a good variable for us. Okay, because what it tells you is the coefficient is very likely to be positive. Okay, so if I want to do a confidence band of 90%, I can clearly say 90% of the time this coefficient is to the right of 0. So this is a positive coefficient and a significant coefficient. Okay, now another example. I just flipped the sign. Okay, so I put this mean as minus 1.5. It does not change anything. Only thing that changes is the coefficient is completely negative. So this would be a negative coefficient, but again statistically significant. Okay, now if you go to another, I increase the standard error to 1 point. Okay, on first glance, what you will notice? Again, predominantly positive. Right? A large portion of this distribution is also positive. In fact, it is about 0.89%, 89% is positive. 11% is negative. Okay? So, in this case, we reject that this is a significant thing. Again, the idea is, let's say my confidence interval is, I'm putting a limit as 90%. So, at least 90% of the curve should be to the right of 0 or left of 0, depending on the coefficient. If the mean is positive, you have to be to the right. If the mean is negative, you have to be the left of 0. But if it crosses that 10%, the area on the other side, we'll say no, this coefficient is not reliable. We don't want to use it. That is the idea of what we are doing when we do confidence testing or computing statistical. So what we are checking is how much area of under the coefficient crosses 0. Okay, this again. If you look at it, many people who don't look at statistics will say, oh no, but 90%, a large portion is to the right. Why are you ignoring it? Because the reason is because if I take another sample, this reduces the, having this area here, reduces the chance that this comes significantly under sample also. So you can think of it as, if I take 100 samples of 1000 records and estimate coefficients, only 89 of them will have this parameter as positive. In the other 11, it will be negative. I don't want such coefficients. I want coefficients that are of the same sign at least 90 times. Again, because I put confidence limit as 90. If I want 95, obviously this will be even worse, right? If I want 95% confidence, this will be even worse. But the idea is we are trying to find coefficients that don't work just on that data, but they work on every other. That's where the variation and standard error comes into the picture, because we want to make sure this standard error tells you how confident the data set is on the value that we are arriving. If that confidence is lower, then that tells you that, okay, if you take another sample, maybe this won't come significant. We don't want coefficient like that. We want to be very sure that this coefficient at least will come 90 times or 95 times or 90, depending on the case, right? If you're modeling travel behavior, number of trips, 90% accuracy, 90% confidence level limit is okay. But if you're, say, investigating a drug for cancer, okay, there you don't want to say, oh, I don't get 10 people will die, that's okay. It works on 90 people, the other 10 will die. You don't want to do that. So what you do there is you have a higher requirement, confidence band. It could be 99.9 in that case. Okay, that makes it harder to pin down. So only very strongly significant drugs will be selected, right? Even with that, right? Even if you think about it, 99.9, especially when you're running models, you know you won't get coefficient significant if you put 99.99 as your significance level for your estimation. But for million people that take a drug, if you don't put it at that level, you still are losing a lot of people. So it's associated with life, right? If we get number of trips wrong, yes, there are consequences, but they are not life and death consequences. So we can live with 90 or 95. So we need to be careful by context on what should be the confidence level that you want to stay. So here I am showing the relationship with 90, 95, and 99 here. So for 90, this would be the 95%. The area would be 1.96 to 1.96. Okay. For 90%, it would be 1.65 to 1.6. As we go larger, obviously. So, but when you run the models, I mean, nobody is doing this, drawing the area under the curve. It takes a lot of time to do this, right? So you don't want to do that. So there is an efficient way of computing it. What you do is you compute the ratio of the coefficient and the standard error. So, for example, I just need to take 1.5 divided by 1.2, okay, and take the absolute of it. If that crosses the 90% level or 95% level that you're trying to look for, then you can say that coefficient is significant, otherwise it's not significant. The reason we do that is if this ratio is less than more than 1.96, it will ensure that the curve is to one side, right? Because when I move 1.96 sigma to the left or to the right, I will not reach 0. So mu, you can think of it as mu plus or minus. If you're doing 95% confidence level, we're doing this. Okay, so if your mu, let's say, is 1.5 and sigma is 1.2. Okay, so when I do 1.5 plus 1.96 times 1.2 plus or minus, the minus will take it to negative value. It is roughly 2. So it would be something like minus 0.9 for the negative side and for the positive side 3.9. Again, I'm approximating it. So once you get a negative value, your variable has a problem. So you have both positive and negative. As long, so that means your curve is crossing 0 with significant area. Again, I'm not saying it's 50%, but it is a significant area. So whenever there is a sign change in this confidence band, we have a problem because it's crossing 0. The 90% area also has 0 within it. Okay. Again, is everybody getting that or no? Let me show you. So, if you take another example, let's say 0.3. Okay. So in this case, plus or minus 1.96. So if you do this band, so the lower end would be the minus, so 2.6, so it would be 0.9. So this is an ideal variable, right? So what we are noticing here is The lower limit is 0.9, upper limit is 0.21. This covers 95% of the area. Okay, so this is an example of a variable which predominantly stays to the right up to 95%. Now, if you have this one, it's this one minus 0.9 to 3.9. So in this case, the 95% area covers minus 9 to 3.9. So there is a good probability that it is negative sometimes, it is positive other times. So this is not a good variable. So if it is, okay, the question probably is something like what if this is 0.0, right? Yes. So the instead of meeting 95%, it is 94.5%. There you can make a judgment call. That is fine.
Would we reduce the confidence interval depending on context and
Yes. So you can. What typically like I do again, there's like I said, it's statistic. So there's no rule that you can force on anybody. But what you can do is you can say I'm looking at 95% as my confidence level, but this variable missed it a little bit. But because I think previous literature has also shown that this variable is significant, and we are retaining it for this purpose. You can justify that. Again, at the same time, you don't want to. You're going for 95 everywhere. You don't want to retain something at 83%, but 94, 93, you can make it. So we have retained sometimes insignificant variables at 80% also, but you need to make a case for it. Obviously, a reviewer will ask, and also you have to support why you're. But for theoretical purposes, this is how we.
is it statistical justification important of the context and the context and
Context and subject knowledge is trumps statistics all the time. It should. Okay, there's no substitute for context and understanding of the problem. Okay, for example, if you're running a safety model and AADT comes out, annual average daily traffic comes out to be significant on the road, that doesn't make sense. I mean, how can you say if traffic increases, crashes will reduce? That doesn't. So you need to recognize those things. So subject expertise is always valid, and you need to think about capturing the variable different. Okay, so statistics is a supporting mechanism for what we are trying to do. But there are some rules that you need to be careful, and if you understand them correctly and violate them, it's okay. The problem comes when you don't understand and then violate. That's why we want to understand this well. So if now you making a case, yes, I understand it. It should be it should be less than 0, but a little bit of it is on this side. So you know what is the consequence of that error or that violation, and still you are willing to take the justification to provide a justification to control for that. That is how you should do. Okay. So now, instead of trying to do these two numbers each time, what I'll do is I will do this. Okay, so this is the easier one. So 5. It's 5 by 4, right? So this is 1.2. So this value is smaller than 1.96. So this will fail the test. This value, the 5, is more than 1.96. So this will pass the test. So again, we started with the curve, we started with positive, negative, but again, we can't do all of this each time you run our model. So we simply do compute beta over sigma and compare it to if it's greater than or equal to the T critical. So for 95%, this would be 1.96. If it's greater, then it's significant. If not, it's insignificant. That's the T test that we do. No. Again, these numbers are provided as columns. Any software you run, they'll give you the beta, they'll give you the column of standard errors, and they compute the T statistic for you. They take the ratio of those two terms and give you that. You just have to check whether it's greater than 1.96 or not, or 1.65 if you're using 90%. Okay, so this is how we do hypothesis. Yes, sure. Again, this is people are used to doing rounded percentage of the day, so they use that. There is that does not preclude you from considering impacts. So if you're doing 90, right, if something is like 91 or more, you are not throwing it away. Right? Everything above 90 is considered. So 91, 92, 93 are also considered. So just people prefer the rounded values. Yes. So you have to mention exactly what you're using. Okay. So if it is significant at 91, so you understand the question between 90 and 95. Okay. So sometimes some variables are significant at 95, they are not significant at sorry, they are significant at 90 and 95, but some are only significant at 90, they are not significant at 90. A better way would be to indicate the retain all of them and say they use the stars approach. They put 1 star, 2 stars, and 3 stars. So 3 stars for variable significant at the 99%, 2 stars for variable significant at 95, 1 star for 90. So you are retaining everything beyond 90. Okay, that would be a better way. That is more accepted way of reporting your results than trying to change the content. Because people are used to using, yeah. So this is I have slides where I show how to compute the test, and these are the bands, the confidence levels. We have 90, critical value is 1.65. It keeps going up as we go in terms of the percentage confidence level. Okay, so the main computation is beta over standard error. So beta is the coefficient, mean over standard error. So in the business file I showed you, this is your beta, this is your standard. All you're doing is the ratio, which is computed as the distance. So you see for the number of persons, the t statistic is 23.9, which is more than 1.96 or even 1.65. Similarly, the other one also, you'll see that this is 6.5. So these are the values per term. Okay, and in SPSS, you get a significance column, which tells you that significance is less than 0.001, which means it's significant at 99.99. Okay. So this information is available in any software. Okay, you have the coefficient, standard error, and exponential. You can use the software appropriately that you're doing with to get that. Any questions?
Actually, I didn't want to, but its values went from minus 1.96 to plus 1.96. Only should be greater than 1.9.
I'm taking the absolute value. So they go, it should be greater than, if it's negative, it should be greater than minus 1.96. If it's positive, the beta, it depends on the beta, right? The beta is positive, you are making sure the whole thing, it doesn't go negative. The coefficient doesn't go negative. If it is, the coefficient is negative, we are looking at the other side. We are saying plus mu plus 1.96 sigma should be less than 0. Okay, so to avoid that confusion, you take the absolute value. So we put t statistic as an absolute value. You won't see anywhere that this being negative. Or let's be here, but we are comparing it to t critical by taking the absolute value, that is the easiest way. The t statistic will be negative when you have the coefficient as negative, but t critical is always positive. That's how you compare it by taking the absolute. Yes, if the coefficient is negative, beta is negative, significant value will not be negative. Sorry, no, significance cannot be negative. It will be 0, which means it's the t statistic is so small that you have no explanatory power from it. So the larger is the t statistic value, the larger is the explanatory power of that variable. Right? If you have very high t statistic, it tells you that the curve is very tall. If you think about the distribution, so tall that you don't have any variation. It's actually very perfectly thin around the mean. So this is the, so I'm showing you the curve here. So 2.184. If you look at the confidence interval and use that, so you get this fact. So you're saying the coefficient varies only between 2.005 and 2.6. So what this tells you is, if I take 95 data sets and estimate the same model with this variable, they will range between this, which is a very narrow range, which tells you that the coefficient is significant. Same thing for this is the 90% for the same. So 90% will be a smaller band than the 95%, because your P critical is smaller, 1.96 to 1.6. Okay. Any questions? So now we'll talk about goodness of fit. So again, as we talked about, we need to figure out when the model is doing well and how do we compare. So there are we can identify when a single parameter is significant or not, but we need to know, okay, how about the whole model, right? So for this, we have three elements we model.
If the range from minus to 2 is real world, it cannot be minus.
No, I mean, some variables are negative. All we are saying is the coefficient should not change sign across samples. If for example,
Here we are actually doing mu plus something in the sigma, is actually we are estimating the expectation based on the mu and sigma value at a particular confidence interval.
yes,
So we are getting the mean value of something which we are interested to find.
yes,
So when it is we are ensuring that it stays on the positive side only means that, because in real world we don't have any negative values.
no, we are ensuring it stays on one side. I'm not biased about positive or negative. All I'm saying is majority of the value should be towards one side. Then I know it is impacting in a particular. See, if I have a variable that is 50% positive and 50% negative, I have no idea what the variable does.
We are interested in direction in which the variable impacts the.
Yes, the dependent variable. Yes. So if I have, for example, I'm modeling number of trips and I'm looking at number of cars. As number of cars increases, I expect it to have a positive impact. So I want the entire distribution to be to the right of zero. Right? That way, it's all positive. If it is 70% positive and 30% negative, maybe number of cars is not.
Instead of number of trips, it is number of trips by public transport and number of cars, then it should have been the other way.
Exactly. So then you want the whole distribution to be to the left of. So now we want to look at goodness of it. So for that, we talk about three Y's. So there is the observed Y, the predicted Y, the average Y. Okay. So we call SST. This is the total error in our model. Remember when we started, we said the dumbest guess is the average. So the total error in your model is given by this equation. Observed minus average. Okay. Then SSE is the remaining error. Okay. So and the third one is SSR. Let me write all of these elements. Okay, there is summation of all of these. These are summed across. So there are three terms. SST, this is the total error. Okay, so it is between observed and the average. Okay, so Y and Y bar. SSE is the remaining error, or sometimes it's called sum of squared residuals. Okay, so this is, we have developed a model and this is the remaining error. This is our prediction from the model. This is the observed. So difference between the observed and the predicted from your model. This is called sum of squared errors. So this is called errors. is the value added by your model. I am looking at y hat minus y bar. How much of the error are you able to explain? This is called sum of squares regression. Okay, so SST will be equal to SSE plus SSR. Okay, total error is remaining error plus the error I am able to explain. So ideally, we want this to go up and this to go down. Because this is the remaining error, we want this to be 0 if we can, this to be equal to SST. That would be our goal. Okay, if SSR goes up, it's good. If SSE goes down, it's good. And now, using this, we define R square as SSR over SST. Okay, so this is what we get in terms of improvement versus total error. Now, if my model happens to be the average model, okay, y hat will be same as y bar. Okay, in that case, SSR will be 0. So that will be the lowest point for R square. R square starts at 0. And if your y hat is a perfect model, okay, y minus y hat will be 0. If I have a perfect model, if I am able to perfectly predict everything, SSE will go to 0. So SSR and SST will be equal. So R square will be. So if you have a perfect model, R square will be 1. If you have the dumbest model, which is just the average model, that will be 0. So your R square will go from 0 to 1 based on this. Okay. Again, sum of square residuals is also printed if you are running linear regression. R square is computed in your software. It's available to you to use. Okay. Does this make sense? Any questions? Okay. So R square equal to 0, SXC is equal to 0. Yes. There's issue with data. So there is an issue with it. It can happen that in some cases you will get coefficients which are contrary to what you expect from. Okay, it can happen. I mean, there are a lot of data sets where that happen. So some of the things you can do is look at the relationship excluding everything else first. Okay, so for example, in your model, maybe there are other variables that are closely interacting with population. So that could be creating an issue. So if you start with only number of cars and one constant and population, maybe it will be positive. And as you keep adding, it flips at some point. So don't add the variable that is making it flip. Okay. So that is in linear regression, that's an important issue because correlation between variables will be a problem. So when you're specifying, you should specify whenever a single variable flips the sign of important variables, I would drop that variable that is causing the flip. Okay? And investigate it further. First of all, maybe something is wrong with that variable or it is highly correlated, so maybe we cannot use both anyway. So don't use them. That would be the way. So R square explains the variance is computed as the variance explained by the model, which is SSR, and divided by SST. That's the total variance in the model that you're trying to look at. So now R square is a good way to compare models, right? So if you have model 1, model 2, model 3 that you develop, whichever model has the higher R square, it explains things better. So you use it. Okay. Now let's think of a case of these models. So R square works very well when you have the same number of parameters, right? So I have three specifications here. I'm looking at number of trips, number of cars, and household size, and the variable perm here represents whether that household is a permanent household or a seasonal. So you can think of that as a big retirement location. So for us, it's an important variable where you will have households from Canada who come and stay only in the winter. Okay, so their behavior will be very different than people who live there throughout the year. So we're trying to capture that with this. So here I have number of cars, household size, and permanent. Instead of number of cars, I'm using income, household size, and permanent. And instead of using household size and income, I'm using number of workers, number of non-workers, and permanent. So let's say I ran all of these three models. Whichever model has the higher R square, I can select that model as the superior model. Okay. Now, what happens when you have more number of variables? Okay, there could be cases like this. Three models. R square values are and number of parameters in the model are 5. So which model would you prefer? So model 1 has an R square of 0.5, K is number of parameters is 5. Model 2 has an R square of 0.55, it has 6 parameters. Model 3 has an R square of 0.552, the number of parameters I'm using is 100. Which is the preferred model? Okay, why second and why not third?
Even if the number of parameters used increases is marginal or negative, the variance it is able to predict doesn't have its impact growing the function.
So if I tell you all 100 of them are significant, so yes, 2 is the correct model to pick. Okay, the reason we prefer models with good R square but not a huge number of parameters is because remember, why are we developing these models? We're developing these models to predict future outcomes. Right? When we're looking at future outcomes, if I have 5 variables in my independent variables, I have to figure out those 5 variables for the future also. I'm telling you that you can. I'm making yes. Realistically, usually you won't be able to because you have 100 that are significant. R square will improve a lot more. But the main reason is the ability to forecast for the future depends on how good your independent variables also are in the future. So if I have for that 0.002 improvement, I don't want to forecast 94 extra variables for the future, right? So it is purely from that perspective. So R square is good, but it does not capture the effect of number of parameters. So that's why we use what's called an adjusted R square. Again, it's built on the R square metric. All we are doing is we are controlling for number of parameters. If your K is very large, I look for okay, is the improvement really worth the number of additional parameters? Okay, so an adjusted R square takes care of this issue. So adjusted R square will help you compare any two models with different number of parameters. You can have 5 parameters in one, 12 parameters in the other. If adjusted R square is not higher for 12 parameter model, you can say the 5 parameter model is better. Okay? So it's again adjusted R square is also computed. So if you can see, it's just using SSC and SST. N is the number of observations. K is the number of parameters. Okay, K is the number of independent variables you are adding. That's how you can compare. This, if you compare adjusted R square, they would look something like this. So for these numbers, it would be like 0.49, 0.53, it would probably be like 0.43. So that would be how the adjusted R square values would look. So it's easy to compare. Then you don't have to worry about additional parameters. Automatically you can make them. Okay. Any questions? Good.
Sir, if that new R square can justify them.
So yes, R square is one of the most misused metrics in transportation and electric field. Okay, so there are cases where you run a model, you get an R square of 0.1. In your research, the reviewers will comment this model is very bad, it doesn't have a results. The garbage comment. Okay, because R square is specific to the data set. Okay, there are data sets where you have only 200 observations or 300 observations and the So overall process is such that you get an answer of 0.9 without adding it. I mean, you add one or two variables, you get 0.9. Some data sets you can add 100 variables, you are not crossing point. And I had models where data sets where I think the best R square I got was 0.08. Again, R square is not comparable across data sets. It is wrong to compare it that. If some reviewer comments saying that this R square value is very low, there is another paper where they got an R square of 0.6, it is a wrong comparison. R square should be used only to compare across that data set. Okay, it is used to identify the best model for that data set. So if your R square when you do one variable comes out to be 0.6, yeah, when you keep adding it will go up to 0.7, 0.8. But if you start at 0.03, it's not going to go to 0.4. So don't use it as an absolute metric. Okay, again, you don't want to be rude and the reviewer comments on it, but you can talk about it saying that our explainable variance is very large and the variables we have, the overall process is such that we are not getting very large, high margin. We have tested different variables. These are not significant. So you can explain it. So R square values is useful to only to some extent. Okay, so sometimes you will have models where n and k are very big. So you have 100 data points, and let's say you estimate 25 parameters. Then R square becomes very high easily. But if you have 1000 data points and your model only has 7 or 8 parameters, R square is not likely to be very high. It can be in some cases, but that also plays a role. So the ratio of n and k, if they are orders of magnitude different, so if it is 1000 to 10 versus 100 to 50, in that case R square will be much higher when you get k closer to 10. Okay, so that's also something you need to think about. So then I want to talk quickly about specification. So here I'm giving you an example model here. So you have number of trips is a function of number of cars and household size. Okay. So if in addition to this, we also want to capture the presence of permanent, whether the household is a permanent household or not. So I can add a specification. So what does, let's look at interpretation for all of them. What does beta 1 represent here? What is the, if somebody who has no idea about what is statistics comes and asks you, what does beta 1 represent? What would you explain? Physically. It should not be a mathematical explanation, it should be a physical explanation. What does beta 1 represent? So if number of cars increase by 1, the number of trips will increase by beta. Right? Same thing for households. What does beta 3 represent? How would you interpret beta 3? So that household is either permanent, which there are only two levels. It's either 1 or 0. Okay? So if it is permanent household, beta 3. Yeah. Beta 3. Okay, so households, so beta 3 represents the difference in number of trips between household that is permanent versus season. Okay, it is the difference. So if everything else is the same, beta 3 represents the difference between a permanent household and seasonal household with the same number of cars and the same number of people in the household. Okay, that's how you interpret beta. Okay, so now I changed the permanent to seasonal. Okay, I cannot add both. Okay, I cannot add both permanent and seasonal, right? Because in fact it's only relative that you can find. So if you add it in the model, if you're running in SPSS or any software, it will drop one of them. Because once you tell the household is permanent or not, you are automatically telling the data the information about whether it's seasonal or not also. Because if a household is permanent, what will be the value for seasonal? If the value is 1 for permanent, the value for seasonal will be 0. Right? So if you have two columns which are linearly dependent, you cannot estimate two coefficients. So you can only estimate one coefficient in your model. So that's why if you have two levels, permanent and seasonal as two categories for each household, only one of those two categories can be in your model. It's like one of them is the default phase. So now I switch that around and I put seasonal. What will be the relationship between alpha 3 and beta 3? If beta 3 is the coefficient for permanent and alpha 3 is the coefficient for seasonal, will there be any relationship between beta 3 and alpha 3? So if permanent increases the number of trips they make by 0.5, what should seasonal do? Reduce the number of trips by the same number, right? So alpha 3 and beta 3 are related. They are just negative feature. Okay, if beta 3 is positive, that tells you that permanent households make more trips. So by the same logic, permanent households are making more trips. What will seasonal households? They'll be making less trips. Okay, so beta naught, beta 1 and beta 2 will be the same across the two systems. Beta 3 will be minus. We will test it in the data set. If you run the model with different levels, we'll see these things. Some of them will really make us very. So this I'm talking about categorical variables here. So you have household with number of cars and household size, and now I want to add the effect of income. And income is given as a 3 category variable: low income, medium income, and high income. Okay. Again, you have 3 levels. So we can only use 2 of those levels in your model. Okay, you cannot try all 3 of them because if you are not low income, if you are not medium income, you have to be high income. So the 3 columns are dependent. So you can only take 2 independent columns from any 3 categories. So that's why you can do different kinds of models. You can have medium income, high income, low income, medium income, low income, high income. Okay, but you cannot have all 3 in any specifications. All these 3 specifications are valid. You can choose any of them. You can run the model anyway. R square will be the same for all 3 of them. Okay, because think of it this way. The information that goes into the model is the same. If I tell them the household is middle income or not, or high income or not, I'm also telling them about low income or not. So this has 3 columns of information. Even though I'm only entering 2 columns of data, the third column is implicit, right? Because it's the same in all 3 of them, they get the same degrees of freedom, same information, so their R square will be exactly the same. Now, will all coefficients be same? Not necessarily. The coefficients will change, right? Because you have here, you have medium income and high income, which means low income takes the value of 0. In this one, high income takes the value of 0. In this one, medium income takes the value of 0. Okay, so based on that, the coefficients beta 3, beta 4, alpha 3, alpha 4, beta 3, beta 4 will change. Okay, there will be a defined relationship. So if low income and medium income has a difference of 0.5, that will hold in all of these. If medium income, let's say you expect more trips from higher income, so let's say medium income is more than low income by 0.5. You will see that relationship in all 3 of them. And let's say high income is more than low income by 2. Just as an example, you will see that difference of 2 perpetuated in all 3 models, but they might not give you the exact same coefficient. Okay, everybody okay with that? Okay. So if you have k categories, so here I am giving an example of 3 categories. So we did 2 variables. So if you have k categories, we can do k minus 1 indicator variables. It can get messy because you'll have a lot of categories. Sometimes income is provided to you in 8 or 10 categories. So then what you can do is group them into some fewer number of categories. Same thing with age. Sometimes they give you age every 5 years. Maybe it's not necessary to try all those categories. What you can do is look at 16 to 24, 24 to 45, 45 to 65, 65 and then so things like that. that you can group these age categories and then reduce the number of categories to be testing in the model. That will help you in specification. Next one I want to talk about is what's called independent explanatory variables. So you'll notice here, instead of using number of cars, I'm using the types of cars. So in the Indian context, it would be better to say number of cars and number of two-wheelers, right? So which is very more common. So let's say here I'm talking about that. There is household size. I am splitting number of cars as number of sedans and number of SUVs. Okay. So what does beta 2 represent here? In this case, similar to number of cars, right? One additional sedan. What is the impact of one additional sedan on trip making, right? So if number of sedans increase by one, the demand or number of trips increase by two. Same thing for SUV. Okay. So now, if beta 2 is larger, what does that tell you? That tells you that sedans increase trips more than SUVs. Okay. Now, let's look at this specification. I'm looking at this specification where I have household size, number of vehicles, and number of SUVs. What does alpha 2 represent here? The coefficient. So these, what does alpha 2 and alpha 3 represent? Basically. That's SUV, right? It's SUV. Okay. So we cannot interpret it based on the number of vehicles anymore. So if number of sedans increase, the alpha 2 represents the change in sedans, effect of sedans. Why? Even though it is multiplied with number of vehicles, because we have an alpha 3 which is out specifically for SUVs, alpha 2 does not represent all vehicles. Alpha 2 only represents sedans. If I increase my sedans by 1, my number of vehicles will increase by 1, but nothing changes in alpha 3. So alpha 2 represents the impact of sedans. Okay? Alpha 3 does not represent the impact of SUVs. Alpha 3 represents the additional impact of SUVs on trip making. Because the effect of if SUV increases, two things change. Alpha 2 also gets it plus 1. Right? Because SUV is also a vehicle. So if you increase SUVs by 1, the change is alpha 2 plus alpha 3. If you increase sedans by 1, the change is alpha 2. Okay, so alpha 3 represents the extra impact of SUV on trip making relative to sedans. If alpha 3 is positive, it tells you people, SUVs have more impact on trip making than sedans. If alpha 3 is negative, SUVs have less impact than sedans. If alpha 3 is 0 or insignificant, it tells you SUV and sedan are the same. We don't need to differentiate. So in this specification, I can actually decide with statistical confidence whether we even need this alpha 3 or not. In the previous one, to estimate a model like this, both beta 2 and beta 3 will be significant because both are somehow capturing the effect of vehicle also. Right? Because if I have 4 vehicles in the house, 2 sedans and 2 SUVs, I put 2 for this, 2 for that. So beta 2 will be, let's say, 2.1, beta 3 is 2.3. Both are significant, but they're close. We cannot test it in that specification. But if in this specification, I'll get 2.2 for alpha 2 and 0.1 for alpha 3, and it will be insignificant. That will tell me, oh, I don't really need to worry about what type of car. Now, if alpha 3 is significant, I know that the type of car matters. So this specification is an improvement. Okay, R square will not change. Okay, this and this will give you the same R square. But in this specification, I can quickly figure out whether I even need the incremental variable or not. Okay, so whenever you have interdependent variables, you should try one common variable because number of vehicles is common to all types of vehicles, and then try incremental variables that capture deviations. That will help you to figure out, okay, do I really even need the deviation or not? Make sense?
If there is a case, here we have number of cars and here we have segregated the class, right? So
Yes.
the same boils down to gender. You don't have number of people,
But you have adults and number of workers, number of non-workers, number of full-time workers, number of part-time workers. There's a lot of variables where you'll have this.
specific to gender, we have only either male or
Yeah, that will be like the first case, permanent versus seasonal. It will be like the permanent versus seasonal. It's a sort, right? So all of these specifications are equal. I'm looking at specific 1 and 2. So this is the relationship between media 2 and media 3. So in this we'll pause here. Again, these specification issues are simply to give you some thoughts when you're running models for your case. So with this we covered linear regression. We'll take a break now and we'll start discrete choice models after that. Okay?